Without further ado, I am very excited to announce our last amazing speaker to close us off on this fantastic event, Hamish Coubray, the director of Howick. Hamish Coubray is the general manager of Roll Forming Services and director of the Howick Group, of which RFS is the product manufacturing arm. He is third generation of the family-owned business. A mechanical engineer by trade, he has been involved in all aspects of the Howick Group business since he was a teen, from machine assembly and manufacture, training, installation, and technical support, to product development, business development, and management. Hamish's passion for always seeking a better, more efficient way to do something is perfectly suited in the construction industry, where there is so much opportunity to break away from the status quo and do things differently. By asking questions like, how can we do things better and smarter, Hamish has proven that when you push the boundaries, think creatively, you can consistently deliver a practical, commercially viable, better result. Please welcome Hamish Coubray.
This afternoon I'm going to talk to you about how we've been putting into practice an idea about compressing timelines using expanding frames. When we go downstairs later on, you'll see this beauty down there. This is our Extender 3600 machine, which is a telescopic framing machine. This machine, we were around about early 2020, we were about to release this into the market, and then it got delayed a couple of years, obviously, where everyone was stuck at home. The initial machine that's supposed to come up here stayed in New Zealand, and we put it into Roll Forming Services, our local manufacturing arm, and decided to play with it. We've added another one since then, so we're running two different sizes. Kind of the idea came about because internal structures are never perfectly square or level, and how do we more easily overcome the as-built environment? When you're working with extremely accurate manufactured panels, how do you make them fit in a space that is not built to the same degree of accuracy? So imagine you could design a panelized interior wall system that could extend upwards, outwards, easily fit an uneven ceiling, or match up to a column that's not perfectly square or where it should be as the design says. At the same time, with internal bracing, keeping all the studs perfectly plumb, and being able to add in details like accurate and square door frames, openings, additional studs for corner details, and plasterboard fixing, or anything else that you might need to add into that structure. So what is a telescopic panel? A telescopic panel is made up of three components: a C-stud, a ribbed internal stud, and a U-track if a deflection head is required. These panels can be made with any combination of these configurations, and they all come out of a single machine, either panel by panel to be assembled to go panelized to site, or as batches of like components. So there you can see the C-stud and the R-stud. So the R-stud is smaller overall dimensions to slide inside the C-stud to give you that adjustability. And then also a U-track if it's required to do a deflection slot on the top. Here's a quick little overview of how the process works. You'll see it again downstairs, but basically the approach of panelizing the telescopic framing is really similar to traditional panelized steel framing. Except we add these extra components in for that adjustability. So you can adjust for a small amount or a large amount if you're limited by access to a building. And here you can see us bringing small panels in through a doorway and just setting them up to fit the space that's there. Okay, and it's that easy, hopefully, every time. So there's quite a few advantages in using this system for non-load bearing walls. I won't go through all of them, but time, which everyone needs more of, is probably the biggest factor in installing these panels, getting them in, and making them fit. So the extender framing started out as a kind of a simple panel idea. Here you can see an early project we did, which is just full high walls with deflection tracks on the top, telescopic studs at 2-foot centres, and in the front there you can see the standard kit of parts that they used. So as an example, you could design a standard panel 10 foot long that can adjust between 8 and 11 feet. It can be flat packed. The top and bottom tracks are both U-tracks, so you can place additional studs where you need them if you want. But very quickly it escalated because everyone wanted more detail. And One of the first projects we did in New Zealand on a large scale was this, Victoria Lane Apartments in Wellington. It was a new build, structural steel frame with tray deck concrete floors, concrete elevated shafts, and this project was the top 12 floors of the 16-level building, which was 100 high-end 2 to 4 bedroom apartments, many of them with differing layouts. So each level was done in 3 stages. First we did acoustically rated corridor wall. This consisted of 3 5/8 top and bottom tracks with deflection header on the top, 2.5-inch studs staggered at 1 foot centres, also telescopic to reach the slab above. And you can see a close-up of how they worked. We also only punched the dimples for the bottom connection on the side where the stud was supposed to go according to the design, so they didn't mess it up. Next were the intertenancy walls, 2.5-inch stud walls with 2-inch air gap between them. Again, telescopic with a deflection header and telescopic on the ends to meet up with the outside of the structure and the corridor wall. These also had diagonal braces in them to keep them square. And here you can see we also added an additional nog near the top for the plasterboard fixing to allow the deflection head not to be interrupted by screws. We also punched additional holes below the bolt holes for fixing to the slab above so they could easily access through with a long bit. And then each apartment fixed height walls with a false ceiling. These were telescopic to the outside parts of the building, to the IT walls and to the exterior of the structure. You can also see on the plan there the little telescopic symbols showing where we had horizontal adjustability. And we also hosted each one of these models that you just saw on a web-based 3D viewer, and we linked these by QR codes on every drawing. So anyone on the site could scan QR code for each stage or the entire model and easily see how the frames interacted, how they connected, which way the bracing was supposed to go. So if they couldn't fully understand the 2D drawings, they had a 3D model to access really easily, and they could look at it. We also hosted standard details for some of the connections the same way. So the guys on site could easily avoid ringing us to ask questions by looking at a model. Oh, here's a little video of how the 3D model worked on the viewer. So you can see we colour-coded the floor plan as well so they could see which way the frames overlapped, and they were all labelled according to the panel. This project was the first project with this client. They're a large contractor. They hadn't used this product or, in fact, any panelised wall framing system before. It was around 220,000 feet of framing. This was flat packed and assembled on site because it was at 10 hours by truck to the site, so it was just more efficient to do it that way. And they came out of it at 50% of their budgeted man hours compared to stick framing it with stud and track. So for the first project with that client, it was a huge success. And we've gone on to do a few more, a couple we're doing at the moment. Here's another project we did with them when the architect asked if we could do a curved wall for one of their projects. I said, sure. And this was the design of the end, which was more than one curved wall as I was expecting. And as you saw in Scott's presentation, we can design a curved panel by overlapping punches with our standard tooling, which is available in all of our machines that are sent out. So anyone that's got an existing machine can add this into their repertoire of design. Here you can see on the right, full height curved wall, which is telescopic, also has a door frame in it, diagonal bracing, and then it has horizontal telescoping to the facade of the building to take up that slack. And here's a couple of other current projects we're working on with the system. So this is 1 Queen Street. This is in downtown Auckland. It is a concrete structure built in 1972, and they stripped it back to the superstructure, point cloud scanned it, and went from there to design a modern, energy-efficient building. They're saying there will be about 50% of the embedded carbon emissions compared to building a new structure in its place. So this project, we are doing the top 6 levels, which is office fit out. You can see kind of the step in the building from where we started there. It is cast concrete construction with double T's. So here you can see a nice little picture of what we did here. We did prefabbed infill panels for the double T's, which they installed a 10-foot section in about 2 minutes. And then we had telescopic framing coming up underneath to meet it with the deflection header to allow for vibration and movement in the floor. Another one is the New Zealand National Archives building in Wellington, which is an interesting one. this building we are doing all the bulkhead fit out. So there's a really high fire rating requirement because it's the National Archives. So we're using telescopic panels to infill around all the structural beams in between the floor decking, the concrete decking system to allow for their fire rating. And there's a couple of the standard details of how those bulkheads all fit in. We're also doing some load-bearing telescopic framing. So these are fixed height but horizontally telescopic to fit in with an existing concrete building with ceiling panels above, with MEP above the ceiling panels. And that's it. Thanks, everyone.
Thank you so much, Hamish. Hang on just a second. Any questions for Hamish? There's a lot of really great examples of how the Howick is being put into work. Okay, we've got one right here. Yeah. The question was, is there a situation where it's more efficient to bring the machine to the site?
Yeah, there can be if it's a remote application. The project, the VLA apartments I showed you at first, it would have been nice to ship the machine down to the site there. That was in the middle of COVID, so we weren't allowed to leave Auckland, but the trucks could. So in that case, it would have actually been a better option to send the machine down and assemble down there. So we would ship the kit of parts, wall by wall, wrapped together, bundled, and they would put them on each level where the panels were to be installed, and they would assemble the panels on that level and then erect them. And what the guys found in doing that is the guys that were installing the panels could leave their apprentices and labourers to assemble the panels because it's a kit set of parts and they could follow the drawings. So they could focus on installing them, and the labourers and the apprentices could build the panels for them, and that worked really well for them.
You have to infill with steel framing. Actually, in this building that we're all in today, we dealt with it. And I'm curious, when you do the scan, like the guys, when we do it, they just cut it here and they kind of fill, and as you know, they're all slightly different.
Yeah.
When you use a scan, how much are you customizing that to address the conditions in the field for each partition?
So for each partition, well, we are generally allowing about 2 feet of adjustment, so plus or minus 1 foot of adjustment vertically, and more so if there's constraints in getting it into the building. So we allow a lot of adjustment to take that out of there. It also reduces the design time, so you're not making all different height walls all over the place. So if we had a 6-inch variation in the ceiling height, we could design all the walls to sit 6 inches below the lowest height and have enough adjustability to reach the highest.
Okay. All right. Thank you so much
No
again,
problem.
Hamish. I really appreciate it.